All right. Hi all. Thought I would do a little video going over this again because I know there was a lot of confusion, possibly caused by me not reading the questions. But let's move on. So this one here, yeah, they give you the example. So I think there was a couple of people going, "There's too many molecules." I'm like, "Yeah, there is," and I didn't think that was that important until I looked and read this question. And so there's only 4 molecules here. So when we go down and read this question, it can only be A and B because D's get loads of more molecules. This has some molecules and some atoms floating about. And so the A and B are the only ones with 4. And so the implication, I think, is that this is at 27, so 127, it's moving faster with more randomness. So I think we kind of get that idea. Now we have to go to these Maxwell-Boltzmann distribution curves. And I think it was Linus brought up, is that speed or is that energy? And I was like, oh, wait a minute. So you're right. We should use speed. However, kinetic energy is usable. So let's show you where I went. I just kind of Googled it around and I got to where was it? Sorry, I was right there. Oh, yeah. Sorry, other Chrome. Okay, so I thought let's take a wee read of this and see what's up. All right. So this is a couple of places I went. This is actually in physics in Khan Academy. So they're using speed, right? They're using speed. So you're right. Speed would have made it easier, maybe to imagine. You can imagine some are going 0 and some are going really fast. There's also there's other little aspects to this. Okay, so let's go. What is the distribution? The air molecules are not traveling at the same speed. Some moving fast, some slow. Right. What is the speed of an air molecule in a gas? We can only ask. So we can ask what the individual energy of an atom is, and we can ask what the average kinetic energy is. So let's make sure we have a distinction between those. So this is number of molecules. This is speed. So this is easier than me saying number of molecules that have that energy, right? I was trying to be explicit and maybe it wasn't really clear. So it's number of molecules versus speed. The y-axis can be thought as given the number of molecules per unit speed, right? Number of molecules moving that fast, maybe. So if the graph is higher in a given region, it means there are more gas molecules moving with those speeds. So here, most molecules are moving at the same speed. This isn't symmetrical. It kind of stretches out further because you're limited by how wide and to the left you can go. So you can only go to 0. So it kind of keeps going faster and faster and faster, but 0 is the limit. And so there's always going to be one not moving, so it's going to stretch out more and more. Okay, there's other aspects to this that you don't necessarily need, but they might help you kind of understand things. So you might think that the speed located directly under the peak of the Maxwell-Boltzmann graph is the average speed of a molecule in the gas, but that's not true. The speed located directly under the peak is the most probable speed. It's not the average. They have other ways of measuring it. They have like most probable speed, average speed, and then root mean square speed. You don't need to have these down. It's interesting though to look at root mean square speed because root mean square speed takes into account that molecules have what's called vectors, so some are moving negatively and some are moving positively, but if you square those numbers you just kind of get a concept of the magnitude. So like if you're moving at negative 3 meters per second, you square it, you get 9. If you're moving at 3 meters per second the other way, you square it, you get 9. So that's maybe a more accurate way of looking at it. That's this root mean square speed. It kind of takes things that are moving in opposite directions, or positives and negatives, and squares it so you just get a magnitude, and you can look at the average magnitude. So we get some value over here, right? And so physicists will use this for like speeds of electrons going back and forth through a wire, because you have to consider that they're going in opposite directions. So what does the area under a graph represent? I think you guys brought this up very, very rightly. So it gives a number of molecules, right? So the total area under the entire curve is equal to the total number of molecules in the gas. So they should be the same each time, right? If we heat the gas to a higher temperature, so you make them move faster, the peak of the graph will shift to the right, since the average molecular speed will increase. As the graph shifts to the right, the height of the graph has to decrease in order to maintain the same total area under the curve. Similarly, as a gas cools to a lower temperature, the peak of the graph shifts to the left. As the graph shifts to the left, the height of the graph has to increase in order to maintain the same area under the curve. This can be seen in the curves below, which represent a sample of gas with a constant amount of molecules at different temperatures. So this is changing the temperature. Cold gas, room temperature gas, hot gas. As the gas gets colder, okay, I think we get that. See, this is beyond, these questions are usually are beyond what the AP is going to ask. This is more the physics of it, right? So we don't necessarily need to go to this. Oh. This is a good question. The change in a gas. A gas is a distribution of speeds that look like this. Which one of the following series of actions could cause the distribution graph to change from curve 1 to 2? So what could cause you to go from here to here? Well, you know, if you go left, you'd have to go higher if it was the same number of molecules. So it must be less molecules, cooled down. Okay, D. Yay. Okay. So that's speeds, that makes sense. I did want to show you kinetic energy distribution, and apologies, that's what I was using, and thank you for correcting me or pointing out that it didn't quite make sense. However, I did feel there was a lot of over-analysis of the graph going on, but that's totally what you should be doing because you're smart teenagers, right? So this is the Maxwell-Boltzmann distribution for kinetic energy. And they do look a little bit different, right? They do look a little bit different. So, most probable kinetic energy, the average kinetic energy is much larger than the most probable kinetic energy. Because you get some that are just going crazy over here, and that messes up. So it wouldn't be most probable. So there's another, I think they've done that wrong. Okay. Most probable kinetic energy is a half RT, which is the gas constant, 8.314 times the temperature. We don't need this, we don't do this anymore in AP. Average kinetic energy, KE average, is 3 over 2 RT. I think what that is just reiterating here, that equation 5.1.0.2, this is a different equation. We don't use this anymore. We can use, it's like sum of all the kinetic energies, right? But this here is making clear that it's only temperature dependent. Kinetic energy is only temperature dependent because the 3 over 2R is a constant, so this is the same as writing KE is proportional to temperature, with 3 over 2R being the constant. Okay, shape of a curve, always the same. The kinetic energy distribution curve spreads and flattens out. The most probable kinetic energy increases. You don't need that. Fraction of higher energy molecules increases. Yeah, this is kind of what we want here. So this is for hotter gases. This is gases changing temperature. So when you have a cool gas, the kinetic energy distribution is far left. I mean, these look very similar to the a little bit different though. but the same, you could kind of position things the same way. And if you were physically drawing them, you could, get away with either, I think. But for the purposes of this, look at, it should be, they'll probably give you in speed. Maybe we can pick some example questions and look at that, okay? I'm going to put this in, I'm going to put these both. So there's molecular speed distribution. This is molecular speed distribution versus, right, there's nitrogen at 4 different temperatures. And then you can compare probable speeds. This is comparing temperatures again. And now this is comparing sizes, right? Xenon, heaviest, nitrogen, then helium. So that's comparing sizes. So then we go to, you can compare the kinetic energy distribution, and they're not showing for different okay, so this is maybe where I got it wrong. The shape of a kinetic energy distribution curve is independent of molar mass. The shape, okay. Okay, so that is where I messed up. So kinetic energy distribution graph. So if the axis, the y-axis, was kinetic energy, it's always the same. It looks exactly the same. So it would be red. I guess if it was hydrogen, nitrogen, helium, oxygen, whatever, it would all look like the red one, but it's only the temperature that changes it. Okay, and then here, when we look at, this is where the speeds can vary, I guess. This is where these graphs can look different in both ways, whether it's mass or whether it's temperature. Okay. Okay, let's go back to this. So that would be A. Alright, let's talk about this one, which has thrown a lot of you. When the actual gas volume is greater than the volume predicted by the ideal gas law, the explanation lies in the fact that the ideal gas law does not include a factor for molecular something. So actual gas volume is greater than the volume predicted by the ideal gas law. Okay, so let's look at what the ideal gas law is really doing. We didn't even do anything there. So the ideal gas law is PV equals nRT. So what do we have to look at for this? We're looking at, I guess, where, if you did a graph of, well, what's R? R equals, what does R equal? PV over NT, so that should be a straight line. So you know that. What's this based on though? How do we get some value for it, right? What are they assuming the size is? Are they assuming it's anything? No, I guess other than the calculated, because the R here is taken into account that, say, 1 mole of any gas at 1 atm occupies 22.4 liters, right? So any gas at this. So I think that maybe all of these are based on that. Like this is probably certainly based on this kind of idea, right? So let's say 1 atmosphere, so STP in 0 degrees, so 273 Kelvin. So the assumption would be that like the volume, whatever volume, 22.4 liters is going to equal, so if we were just looking at volume, it would be nRT over P equals number of moles, let's say it's 1, times R, which is 0.0821 times T, 273, divided by P, which is 1 atm. So I guess the assumption of the gas law is that this is true. Now that's not including any calculation for volume. That's imagining that there is no volume from the only volume that's present is the shape of the balloon. There's nothing else in there. I know that this is where you guys are, some of you are kind of like tripping out, but the assumption is that in the balloon it's just points. And so the balloon is going to fill up to 22.4 liters at STP. That's the assumption. So who does this work for really well? So STP is quite cold, relatively speaking. So STP is 0 degrees Celsius. That's quite cold. And then 1 atmosphere is that high pressure. It's kind of mid pressure, I guess. So this is not, under these conditions, most gases do this. Right? Most gases kind of behave reasonably closely, ideally. You have to put in a little factor. That's where we get to the Van der Waals gas equation, right? So the Van der Waals gas equation Libra. Okay, so the Van der Waals has got NB and then some AN squared over V squared. Okay, so there's a lot going on. We derived the ideal gas equation from a model in which the molecules are non-interacting point masses. So the volume of an ideal gas is the volume occupied by gas whose individual molecules have zero volume. If the individual molecules of a real gas effectively occupy a volume B over N, what's that N? Number of moles, number of particles or something. Doesn't matter. Then N moles of them effectively B over N times N over N is NB. Van der Waals equation says that the volume of a real gas is the volume that would be occupied by non-interacting point masses plus the effective volume of the gas molecules themselves. Van der Waals equation says that the volume of real gas is the volume that you'd occupy plus the effective volume of the gas molecules themselves. So when you're doing the ideal gas law, you'd have to add in the volume. If you really want to get an accurate picture, you have to add in the volume of the actual molecules, because you think it's 22.4 liters and it's going to sit there, but it's not, because you're like 22.4 liters is the volume that would be occupied if they were point masses, but if it turns out they're actually tennis ball sized, then they're going to push out on this, creating more pressure, striking with more force, and making V actual larger, greater than 22.4 liters. So the standard is set, the standard 22.4 liters is set maybe for a gas that is a pointless, non-interacting, right? Doesn't interact. So everything's kind of based on that. Now at STP it doesn't work that badly, but if you want the ideal gas law to work really well, you want it in a big container and you want a small gas moving fast, and then your numbers work right. Now you might think, wait, what are we talking about here? Now remember what a lot of this is about. This is a lot about the steam engine, the combustion engine, fuel generation, gas has been used to turn turbines. This is how your car goes, right, by the movement of gases around. And so they're usually at high temperature, also usually high pressure. So there's multiple factors you have to take into account. Okay, in that 22.4 litres again, let's say we've actually got H2O. Same number of particles, but now we find that they are sticking together. And so you would calculate this volume ideal, 22.4 litres, number of moles is 1, temperature is 273, R is 0.08206 based on the fact that this is true for everything. 8206, sorry, and then what am I missing? Pressure, again, is going to be 1 atmosphere, so we're all just pushing against this set amount of atmosphere from the sky, right? And so if I calculate this thinking that they're not going to stick together, then they're going to be bouncing around much more. They're going to be bouncing a lot and hitting off the sides of the balloon and causing 1 atmosphere of pressure. But if they're sticky, they're not going to be bouncing off the sides of the balloon as much. They're going to be sticking to each other, and the atmosphere from outside is going to push in more and reduce this volume to something slightly lower than 22.4 litres. I hope I've done that signage right. V actual is bigger than 22.4. No, V actual is smaller. Sorry. V actual is smaller than 22.4 litres. Okay. All right, number 3. Okay. I don't like this question because they're mentioning the products, and I think that was where we hit some confusion. None of these are products. I don't see anywhere in this that explains what the products might be. I have no idea what they are. The products might be polar, they might be non-polar. I don't know. That's what makes this annoying, because they're asking about the products. I'm like, I don't know what the products are. So we have to kind of look and see what are they asking about. Well, they're saying that this thing is polar. So let's draw it. They're saying that the silica thing, silica gel, polar. They're saying that they're going to now put it into a solvent which is 50% polar and 50% slightly polar. This is the I mean, hexane is really non-polar, to be honest. Let's just call it kind of non-polar, right? Hexane, non-polar. Oops. No. 50% non-polar. And they're saying there's the solvent front and there's the products there. Now, again, the reason I don't like this question is I don't know if the RF value is going to change. I presume the RF value is going to change if they change the solvent. So I don't like this for multiple reasons. However, you have to deal with this. You have to deal with the fact that sometimes you're going to get a question which is just not very well written, right? So they're saying, how do you make this go lower? On paper, on stationary phase. So because I don't know if the things are polar, the products are polar or non-polar, I can't use that idea. I have to make the actual solvent. So there's the solvent front with a 50-50. With a 50-50 mix, right? Solvent front goes that high. And so these go up proportionally. Their RF value would be whatever, like 0.9 and 0.8 or something, because they go up like 9/10 of the way and this goes up 8/10 of the way. To make these go lower, what I would do is say, well, I don't want the solvent to go as high. Right? I don't want the solvent to go as high. I want to lower the amount, the height that the solvent goes. I want the solvent front to be more like there. So in order to do that, I don't want the solvent to go up this as quickly. So I'd make this more like 75% non-polar and then 25% polar. I'd reduce the amount of the polar thing. Because the polar solvent will be attracted up the polar plate. So if you make it less polar, it won't go up as far, and this won't go up as far. But I don't like it because I don't know what these are. Okay. B is the answer to that one. Okay, student uses visible spectrophotometry. Okay, I think we kind of got this one. We got this far. Let me show you the Beer's law. So let's say we were using that's a really high concentration. A high concentration has a high absorbance. Let's look at that. A high concentration here has a high absorbance. So if I go down in concentration, the amount that is absorbed goes down. More is transmitted. We can see transmittance is high, and then it goes lower. So it's all about what we're looking at. Transmittance, the amount that gets through, or absorbance, the amount that doesn't get through. So we tend to look at absorbance. So over here, right, you have a more passing through. This is a dilute solution, this is concentrated. So this number here, its absorbance is only about 0.21 or something. But according to your best fit graph, it should be more like 0.28 or something around here. So it's letting more light is passing through than is expected. So why is more light passing through? Why are there less ions than you think? Because when you filled up your little bottle of stuff, you maybe didn't clean it out, and some of the volume was water, and you've diluted your solution even more. So there we get to A, right? That's A. There must have been distilled water. It's also asking you what mistake would a kid have made, right? This is the kind of thing that would happen in the lab, and you'd be like, why are my numbers off? And I'm like, well, did you dry out your cuvette? And you'd be like, no, I don't know. It was someone else's job. Like, okay. All right, let's look at number 5. This is an easy one, I think. Based on the structural formulas, which of the following identifies the compounds that is more soluble in water and best helps to explain why? Well, the one that looks like water. Like dissolves like. Hydrogen bonding from the O to the H, right? Propanol, hydrogen bonds. Yay. Okay. So yes, this topic is kind of a beast with these look difficult, but I don't think they just look a bit difficult. These ones are a pain. I don't know what to tell you. They're just a pain. Every one I've seen of these is like, why are you asking it like that? These ones, I can feel your pain, but you just kind of have to find a rule. Right? When they're talking about volume, they must be talking about volume. Okay, this one here, and then, okay, now we get to, under which of the following conditions the temperature and pressure of 1 mole of the real gas CO2 behave most like an ideal? So, not sticky, not very many. So moving fast and not a lot of particles. So no time to stick and no reason to bump against each other. So highest temperature, lowest pressure. Check the other 800s. Yay. C. Alright, this is the same one. So highest temperature, lowest pressure. Okay, photoelectric effect. Photoelectric effect is essentially ionization energy, right? If I have an atom on a surface and I've got a bunch of electrons here, this could be sodium maybe, 281, yeah, sodium. This electron here will not move if I hit that frequency at it. If I up it a little bit more, So I could fire 25 zillion billion of these, nothing would happen. It doesn't accumulate. But if I add one that has enough energy, bing, it'll leave. And that E equals H nu equals ionization energy, i.e. the first ionization energy. Okay, that's the photoelectric effect. The photoelectric effect also is how things can kind of conduct electricity just by shining light on them. That's handy. So, I mean, again, it's asking about photoelectric effect, but really what's it asking you? It's just asking you to do a really straightforward calculation. Here's an energy. Find the frequency. So like, okay, E equals 3.3 times, how many sig figs? 2, 10 to the, 10 to the negative 19 joules. And you know that E equals H nu. So nu equals E divided by H, which equals 3.3 times 10 to the negative 19 all over 6.626 times 10 to the negative 34. Okay, so I want you to look at this and make sure that you can kind of do a little bit of mental math. So I like to ballpark so I know that I haven't done something funky in my calculator and missed it. So for this I would do roughly 3.3. You know, you're talking about 6.6. That's roughly double. 3.3 is roughly half of 6.626, right? This is a little bit over. This is a little bit less than a half of this. But sig fig wise it isn't. So this can become 0.5. 3.3 divided by 6.6 can become 0.5. Negative 19 minus negative 34 becomes negative 15. So you've got 0.5, this is your mental math, times 10 to the negative 15, which equals 5 times 10 to the 14. And that's your answer. Okay. So that would be C. Okay, let's take a look at 9. A student performed a fractional distillation. So that's when you heat stuff up, a bunch of it boils off, and then, like, let's say you've got, so there's two things in here. So this would look like, yeah, this would look like alcohol and water. Ethanol plus water. So if I was boiling this off, slowly heating up, if I was slowly heating this up, So heating it up, heating it up, heating it up, heating it up. What would happen at some temperature? So ethanol, when does ethanol boil at, do you think? I don't know, maybe 65 degrees Celsius. Definitely below this, which is 100 degrees Celsius. So we're going to have 2 points here at 65 and then another point at 100. And so at 65, not heating up anymore. Mixture's not heating up. What's happening now is bonds are breaking. This is heating. This is breaking inter bonds, right, between the alcohol. And then we heat up again, we get to 100, boom, and then the water boils. Why does the water boil at a higher temperature? Because it's got stronger bonds. Right? Stronger bonds. So you get alcohol here, alcohol, and here you get water. And they're saying it's C7H16 and CH18. So that's CH18 because of LDFs. More LDFs, right? So D, beta C. Yeah, D. Let's check the answers. Propanol, C, 5, D. Yay! Okay. M is an unknown metal cation with a +1 charge. A student dissolves the chloride of the unknown metal MCl in enough water to make 100 ml of the solution. The student then mixes the solution with AgNO3 solution, causing AgCl to precipitate. Okay. Student then mixes the solution with AgNO3. Okay, it's very clever, these things that they do. You don't know what it's a metal chloride, you don't know what it is. Let's find the number of chlorines in it. Then the number of chlorines, because you know it's a +1 metal, will be the same as the number of metal ions. So if you know the moles of chlorine, then you know the moles of M. Student collects the precipitate, so that's the solid formed. So let's draw what's happening. So into here is dissolved MCl. So in here floating around, you've got M positive and Cl minuses. So let's say I've got 3 Cl minuses and I dissolve in here AgNO3 AQ. That means I have floating around Ag, probably loads of them, NO3s, and each of these is going to have an NO3 floating around it. These are all positive, 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 negative, negative. Now 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So what you'll find is you get this precipitate, which is clumps. Stuff will fall to the bottom and crystallize, and it'll take that one, that one, that one, will react with that, that, and that. This is kind of breaking into unit 4, but what's happening is the Ag positive, AQ, is reacting with the Cl minus that's there, AQ. Where did this come from? This came from the M, and there must be the same number of M's as this. Equals the precipitate, which is AgCl solid. That's a precipitate. Precipitate. Okay. Which of the following best describes the AgNO3 solution? All that and they probably don't want us to do anything. Very annoying. So there's Ag positive, dissolved, so separated. Ag is separate from NO3 and it's surrounded by the oxygens of OH2. That looks not bad, and this is surrounded by the H's. That looks good. Okay, what's different about this? Oh, there it's the negatives and there it's the positives. I didn't even see that. There's the positives. Okay, so not B. No, not C, because it's negative to negative. That's oxygen, remember, that circle. Okay, we're good. We know that it is A. All that. Tell me they want us to do something with this stuff. No, they don't. We should definitely hit that one though, because I don't know why they're not asking a question there. Alright. Which statement correctly compares what occurs when molecules absorb photons in the microwave region? So, what do microwaves do? Microwaves spin. Infrared vibrate. So, microwave photons cause the molecules to increase their rotational, whereas infrared causes the molecules to increase their vibrational. Yes. A. And that's it. Alright. Holler at me in tutorial or whatever, or email me, or yada yada yada.